Fluorescence lifetime imaging or FLIM in the time and frequency domain. The differences in fluorescence lifetimes in luminophores can be used as an imaging technique called FLIM. This can be achieved both in the time and the frequency domain. Established examples of time domain equipment are point-scanning TCSPC systems. These point scanners count the emission photons in time, allowing you to reconstruct a luminescence decay curve. This makes TCSPC suited for mixed, fast, and weak emission signals. On the downside, the recording speed of the process is slow due to its point-scanning nature. One frame of 1,000 times 1,000 pixels can take up to several minutes. And because it depends on single photon counting, it has a limited dynamic range. To prevent under- or overexposing, it has to be tuned for either dim or bright signals. Another kind of time domain FLIM uses a digital image sensor. In this setup, the sample is excited by a period train of rectangular light pulses. Each excitation pulse results in a slightly delayed, weaker emission signal, starting with a sloped rise of the emission intensity giving the rise time, and a decaying emission after the excitation light has been turned off giving the fall time. Repeatedly integrating over the same narrow section of the decay curves leads to the first image. Then, the integration interval is slightly shifted to integrate over another section of the decay curves, giving the second image. This section-wise integration is repeated until the whole decay curve is sampled. The limitation of this approach are the shortest possible exposure times of image sensors. The shortest known exposure time at the release date of this video is about 120 nanoseconds. By the development of a novel, fast, modulatable CMOS image sensor, the QM-FLIM2, the so-called frequency domain method became more attractive. In this frequency domain approach, the intensity of the excitation light is continuously modulated using sine or square waves. The modulation source is the camera, which provides modulation frequencies ranging from 5 kHz up to 40 MHz, as well as the signal for dark gating. Using a sinusoidal excitation waveform, the emission waveform is also a sinusoid with the same frequency. It is delayed in time and shows a decreased amplitude, a decreased constant component, and a decreased modulation depth. By comparison of the excitation and emission sinusoids, the time or phase shift can be determined. The phase angle, phi. Also, the excitation and emission amplitudes, A excitation and A emission, become clear, and the constant components, B excitation and B emission. These characteristic parameters can be determined by sampling and reconstructing the emission signal by a kind of half-wave integration measured at least 4 different phase angles. The first half-period integration is done at a phase angle of 0 degree, giving the image I1. Subsequently, the next half-period corresponds to a phase angle of 180 degree, resulting in image I3. If then the onset of the camera integration is shifted by 90 degree and the detection is repeated, the first integrated image I2 will correspond to a phase angle of 90 degree, while the fourth image I4 represents a phase angle of 270 degree. By repeating these integrations during a given exposure time, a sufficient amount of light can be captured to obtain a better signal. Finally, a sine curve is fitted into the measured values in the images I1 to I4 for each pixel. This sine curve provides the phase angle phi, the amplitude A emission, and the constant component B emission, which are used to determine the corresponding fluorescence lifetime values. These lifetime images extend the information obtained by common intensity images. The reconstruction of the emission signal by means of half-wave integration requires a fast modulatable image sensor. This is where the modulatable high-frequency sensor Flim 2 comes into play. It was developed by CSEM and PCO from 2007 to 2012. In this unique image sensor, each of the 1008 times 1008 pixels has two charge collection areas, tap A and tap B. An externally applied two-level modulation signal controls whether the generated charge carriers pass through tap A or tap B. By modulating the excitation light and the image sensor at the same frequency, specific phase shifts can be measured in each pixel. At phase 0, tap A is active. All charge carriers are collected in charge bucket A. This is image I1. At phase 180, tap B is active, and all charge carriers go to charge bucket B, resulting in image I3. This kind of charge swing enables the simultaneous record of I1 and I3 in the same camera exposure, creating a double image. The image sensor modulation is shifted relative to the excitation light. Then, a measurement is performed at a phase angle of 90 degrees. The charge carriers collected in tap A create image I2. Tap B samples the information at a phase angle of 270 degrees, creating image I4. At a maximum modulation frequency of 40 MHz, minimum half-period integration intervals of 12.5 nanoseconds can be achieved. So this is what makes the PCO Flim camera a versatile frequency domain Flim system. It can be used for the measurements of a huge range of luminescence lifetimes from tenths of microseconds down to 100 picoseconds. The PCO frequency domain Flim system is best in its class because it covers the largest range of lifetimes from tenths of microseconds up to hundreds of picoseconds. It's easy to apply, it has the highest resolution and the highest frame rate of the available Flim systems at the moment, and its price performance is hard to beat. PCO Flim is the perfect Flim system for fluorescence lifetime imaging. Fret measurements, dynamic live cell experiments, optical chemical measurements like optical oxygen measurements, and more. For more information, please visit www.pco.de.